The Brain Simulator 2, the Universal Knowledge Store, Part 2. In this video, I'll cover the structure of knowledge in the Universal Knowledge Store, and I'll cover learning algorithms in the next video. If you haven't watched Part 1, I encourage you to do so first to help you get the most out of this video. Here are the topics for this video. First, a little background in the design philosophy. Then, the inputs and outputs to the knowledge store, instinctive knowledge, searching and adding to the knowledge store, and special values I'm using inside the knowledge store. Many researchers focus on a single aspect of artificial intelligence and have made remarkable progress in many areas. My approach is to address the end-to-end scope of artificial general intelligence and to focus on a small number of use cases with just a few words, shapes, and actions. Hence, the entity Sallie lives in a simulated two-dimensional environment and has only a few behaviors. At the same time, interaction with the environment with multiple senses is one key to the appearance of understanding. For example, you understand a cube in ways beyond any mathematical or dictionary definition because you've seen them, touched them, stacked them, dropped them, etc. So the Universal Knowledge Store is designed to integrate information from different types, from different sources as efficiently as possible. Looking at the Universal Knowledge Store in greater detail, let's start with the inputs and outputs. Inputs to the Universal Knowledge Store are Sallie's senses, currently vision and hearing. Touch is also available but not yet connected. Vision is handled as shapes and colors with positions, while hearing is handled in phrases. Right now, Sallie has a single positive or negative reward input. The output of the Universal Knowledge Store connects to Sallie's functionality, which is currently limited to the ability to speak, move forward, and turn. Internal to the store are situations which combine input patterns, outputs, and rewards, so Sallie will be able to learn new behaviors. There are also short-term memory capabilities wherever they are needed. To get the knowledge store started, a few things are added at startup with the add thing method, which creates new things with a label and a single parent. We might consider these things to be instincts or an overall internal brain structure. Below the root thing are the primary divisions of information, which I'm calling action, sense, situation, and outcome. We can see these in the knowledge store display after it has been initialized, but before Sallie has been allowed any interaction with her environment. Actions are physical actions which Sallie can take. These are presently limited to moving, turning, and talking. Senses receive information from vision, hearing, and other potential senses from other brain simulator modules. Visible things include points, colors, shapes, with audible things including words and phrases. Outcomes are a measure of the desirability of a particular action. At the moment, outcomes are limited to either positive or negative, but future development could allow for a more nuanced reaction, which represents the basis for emotion. Two words are currently coded directly to outcomes: good for positive and no for negative. Let's follow through the process of hearing phrases to see how the knowledge store creates things and links. There are two loops. In the first, whenever a word is encountered, it is added to the knowledge store if necessary, and a reference is added to a sequence of words in a short-term memory temporary phrase. In the second loop, when the end of a phrase is detected from a pause, the short-term memory phrase is matched against previously stored phrases with a find similar method. If the phrase is not found A new phrase thing is created with ordered references to the words in the sequence. If the phrase is found, it is fired, which will cause any associated action to happen. To see this in action, we'll use the world simulator to send phrases to Sallie. As words arrive at the knowledge store, you can see things added and a temporary phrase is built in short-term memory. When a pause indicates the end of a phrase, the temporary phrase is matched against stored phrase things, and if no match is found, a new phrase thing is created and the temporary memory is cleared. Here the phrase, "What color is this?" has been added. The brain simulator is set to its slowest speed so you can see the process in action. Now the steps are repeated and the phrase, "This color is black," is added to the store. Now the phrase, "What color is this?" is repeated, and you can see that as words and phrases are heard more than once, the use counts increase. This process creates a thing for every unique phrase which is heard, and we can think of this as analogous to your brain's intermediate memory. The process of pruning similar phrases and creating long-term memories will be discussed in the next video. As I mentioned in the previous video, a thing may have a value stored in it. If it does, the value is displayed after the use count and any references. At the moment, word things contain the spelling of the word in their value, but this isn't actually necessary and will be removed in a subsequent development iteration. Here, the word thing for black has the label WBlack, a use count of 1, and its value is the spelling of the word black. Note that phrases don't have any value. They are defined by their list of references to word things. There are plenty of ways that a knowledge store could include color information without using the thing's value property, each idea with its own strengths and weaknesses. For now, colors show the hex value for the RGB of the color. Here the color labeled C4 has an RGB hex value representing orange. Color use counts are typically large because they are incremented every time Sallie sees that color. Our brains can remember the locations of physical objects around us, and it is likely that internal locations are in terms of more or less polar coordinates with a direction and a distance. Because of the way your eyes work, directions can be very accurate, while distances from you are usually much less so because they are estimates based on the differences in images from your two eyes. As you move, all these coordinates need to adjust themselves properly, so when you walk past an object, you have a pretty good idea where it is, even when you can't see it anymore. We can only speculate how this might work in your brain, but I implemented this process in the brain simulator by creating a software object which supports polar coordinates. Here you can see that the values of these point things in the knowledge store update themselves properly with Sallie's motion. In a few lines of trigonometry code, Sallie can do what a portion of our brains likely do with many millions of neurons. That's all I have time for in this video. In the next video, I'll cover how Sallie can learn to associate words with objects and actions. I hope you'll subscribe to be notified when the next videos become available, and to go to http://brainsim.org to try out the software for yourself. If you found interesting information in this video, please share it with your friends and colleagues. Thanks for watching. For more on this timely topic, read my new book, Will Computers Revolt? Preparing for the Future of Artificial Intelligence. Available now at Amazon and book retailers worldwide in paperback, hardcover, and ebook editions.